Dear friends, welcome to another episode in the Dynamics of the Earth series. That our planet Earth is a highly dynamic planet can be understood from the fact that the height of the mountain chains like the Himalayas is still increasing, though by very small amounts every year. It can be understood from the fact that earthquakes occur around the Pacific Ocean throughout the year, and sometimes they cause very huge damages and loss of life. Earthquakes are also distributed along some zones where the destruction is considerable at some intervals. The recently observed tsunami in Japan is another evidence that our Earth is a dynamic planet. The tsunami is a result of undersea earthquakes which causes the movement of the bottom of the ocean, and that is transmitted into the water, that causes huge waves to hit the Earth's surface at the ocean margins. The dynamism of the Earth is explained in terms of lithospheric plate movements, as we have seen in our earlier episode. We have already discussed how the dynamism of the Earth is explained by the theory of plate tectonics. We have seen how the uppermost surface of the Earth is divided into a rigid layer of many fragments. These many fragments of the lithosphere move past one another and cause disturbances on the Earth's surface. The movement of the lithospheric plates or plate fragments are controlled by the internal forces. We shall be talking about it shortly. The plate margins, as we have discussed, are of three kinds: constructive or divergent plate boundaries, where new lithosphere is created and then moves away from the ridge crest or divergent plate boundary; destructive or convergent plate boundaries, where the older lithospheric plate is destroyed by subduction below another lithospheric plate and the two plates come together; and conservative or transformed plate boundaries, where without any creation or destruction the two plates, the two lithospheric fragments move past one another. The types of plate boundaries will be discussed in some detail now. The divergent plate boundaries are observed mostly under oceans along the mid oceanic ridges, while some of the divergent plate boundaries are also found on continents. Along divergent plate boundaries, a new lithosphere is created by partial melting of the asthenospheric mantle. This comes up to the surface, cools down and forms by partial differentiation the lithospheric mantle and the oceanic crust. This oceanic crust, when it cools down below the Curie point or approximately 700 degrees centigrade, is magnetized according to the ambient magnetic field of the Earth, and then is split apart and moves away from the ridge crests. After some time, another new lithosphere forms, again it splits and gets magnetized during the ambient magnetic field of the Earth. The opposite magnetic polarities or magnetic intensities indicate that the polarity of the Earth's magnetic field, the north magnetic pole and the south magnetic pole, gets reversed through geologic time. Though this reversal has been established to happen, the exact reason for this reversal has not yet been established. As the new lithosphere forms at the ridge crest and moves away from one another, the width of the magnetic anomaly stripes varies according to the spreading rate. From the various mid oceanic ridges like the mid Atlantic ridge, the East Pacific rise, the Indian Ocean ridge, etc., it has been established that there are three possible rates of spreading against the divergent plate boundaries on the ocean floor. The fast moving plates or fast spreading ridges, they move at around 90 millimeters per year. Between 50 and 90 millimeters, the spreading rate is called intermediate spreading rate, while below 50 and above 10 millimeters per year is known as a slow spreading ridge. The topography of the ridge crest and the slope on the flanks is also controlled by the spreading rate. When the spreading rate is slow, there is a very deep and highly irregular topography along the ridge crest, a very deep valley and a highly irregular topography along the ridge crest. In case of intermediate spreading ridges, the median or axial valley is moderately deep with not many irregularities, and in case of fast spreading ridges, the median valley is very sharply defined, occupying only the top of the ridge crest, and the slope is very gentle on either side. This topography helps us in understanding the features or processes that are active below the ridge crest. The reason behind the variation in topography of fast spreading through intermediate to slow spreading ridges can be attributed to the processes active right below the ridge crest, the mantle. The fast spreading ridges, they generally have a continuous supply of material, while in case of the slow spreading ridges, the supply of material from below the ridge crest is interrupted at times. The divergent plate margins on the ocean floor are also characterized by high heat flows because of the outpouring of the mantle there forming the new lithosphere. They are also characterized by slightly below normal gravity anomalies. The overall balance of the gravity anomaly is more or less uniform over the ocean floor, and these areas are zones of formation of metallic sulphide deposits. We will be discussing shortly how metallic sulphide deposits form on the divergent plate margins on the ocean floor. The divergent margins that occur on continents are similar in tectonic scenario to the mid-oceanic ridges or divergent plate margins on the ocean floor, but their new lithosphere is not created. There are many stages of evolution of continental divergent margins. If we look at the eastern coast of Africa, we will see that there is a intersecting or anastomosing zone where crustal thickening is taking place, and probably the easternmost part of Africa called the Somalian subplate will split from the African mainland sometimes in the future and form a sea between the African mainland and this part of the African continent. There are examples of such divergent margins elsewhere that are slowly evolving into ocean basins. If we look at the Red Sea, at the bottom of the Red Sea there is oceanic crust, but this was the Arabian plate and the African plate, which are separated by the Red Sea, were once together. Along the Red Sea, a divergent plate boundary has evolved, and that gradually split the continental crust first and then the oceanic crust, so that the two plates got separated with the ocean pushing into the gap and forming the Red Sea. The dynamics of divergence of plates is not yet very completely understood, but it was suggested by W. Jason Morgan in 1972 that a series of hot spots or regions of very high heat flow rise from the core mantle boundary, and when they are aligned along a line, they cause the spreading out of the asthenosphere and consequently the lithosphere above it. The spreading out of the lithosphere plate above a line of hot spots cause the development of divergent plate margins. or there is another alternative theory of explaining the divergent plate margins, which is known as the propagating rift hypothesis. The convergent margins between plates is the region where one plate is generally subducted and destroyed as it reaches deep into the mantle. Convergent plate boundaries, especially those around the Pacific Ocean, along the Himalayan mountain belt, along the Alpine and Zagros mountain belts in Turkey, they are sites of great earthquakes. The convergent plate margins, as we have briefly discussed in the first episode, are of three types. One where two oceanic plates come together and the older and denser one goes down. A second type where one continental and one oceanic plate comes together and the continental plate, because of its lighter material, has a higher buoyancy and the oceanic plate goes down. And the third variety is where two continental plates riding piggyback on oceanic crust come together, converge together. This can be exemplified by the movement of the Indian plate towards the Eurasian plate. Once India was part of the southern supercontinent, the Gondwana land, and then the Indian plate moved northwestward and northward, so that the leading edge of the Indian plate, the oceanic portion, got subducted below the Eurasian plate, and finally the Indian continental part came close to the Eurasian plate and collided. During this collision, the sediments deposited in the intervening ocean, the Tethys Sea, were squeezed up to form the Himalayan mountains. During this collision process, part of the Indian continental crust, because it was moving very fast in a northerly direction, part of it went below the Eurasian plate. However, the buoyancy, the equal buoyancy of the two prevented further subduction, but during this small period of subduction, the thickness of the continental crust north of the Indian plate below the present day Tibetan region became very high. The approximately 70 kilometer thickness of the continental crust below the Tibetan region is explained by this fact. Thank you.